welcome to everyone to this next in the series of our Innovations in EDA webcast. Let's go ahead and get started. On the agenda today, we will be starting off by discussing the challenge of RFIC verification. And then we're going to introduce a new RFIC verification flow based on behavioral models. We're going to go back and review memory effects, which was discussed on in a webcast that we did in February. But according to the list of attendees we have, most of you were not there. So we're going to review a few key points there. We'll take a brief look at a historical survey of different behavioral verification models that have been used in the past. And we're going to talk about some of the application details on this new verification flows, including some important cautions that you should keep in mind. Finally, we'll wrap up with a couple of system verification examples, an LTE uplink transmitter and amplifier digital predistortion example. And we'll wrap up with summary and conclusions. So I'm going to start off by proposing that there's really two main things that make RFIC verification quite a difficult task. And the first one is that modern radios are not simple analog circuits like you may be used to radios being in the past. In fact, what you're going to find in a modern CMOS or bi-CMOS radio is that there's a huge mix of analog, RF, and digital and mixed signal circuitry. And these circuits they're complex, but they also interact heavily with each other. And this makes verification of the designs quite challenging. Part of the problem that comes in as a result of that is that different tools are going to be used to analyze and design different parts of the radio. This means that you don't have a single tool that runs the entire radio in a single simulation. That may be a brute force, very long sim just to verify that it's connected up. So the second fact that we're going to talk about is that the signals that are going through modern radios are extremely complex. Some of the examples that you see here are the most obvious one is LTE and LTE Advanced. These signals are not readily available or even familiar to circuit design engineers typically. They're typically being handled at the system level with yet another set of tools different from the ones that are used in the design community. So these two issues of complex design and complex signals makes verification quite a difficult problem. So let's propose a way to address this. And basically what we're going to propose is to take your circuit designs, which are done on the Linux environment. In this case, we're working in the Cadence environment. And let's build a black box behavioral model and use that for verification. Now, that verification is going to be run on the Windows platform, and we'll talk about why that is in a minute. So let's take a look in a little bit more detail on how this flow works. So we have basically two tools that we're using here in this flow. On the Linux side, we're using GoldenGate, and in GoldenGate, we're going to have our design, our detailed transistor level design, and we're going to specify ports and kind of model characteristics for export. And then we actually run the simulator. We actually exercise the simulator to produce this fast circuit envelope black box model. On the system level side, on Windows, we're going to then take that model, which is a file, and place it, parameterize it, and select the ports that we want to use in our system-level simulation, and then we run it inside of our system-level test bench. So basically, the model creation is done on Linux. The model consumption and usage is done on Windows. So this is kind of the key slide here. So we're going to talk about the key features. So I know that this approach of using a behavioral model as a verification tool has been used extensively in the past, and we're going to talk about some of the history that's been done. But this particular flow is quite powerful, and I think the reason it is in the details of how it's done. So let's take a look at what's available here. So on the model creation side, the nice thing about the model creation is done natively in the design environment where the designer is working, and just as importantly, perhaps more importantly, it's done by the circuit designer. So he's the expert at using the tools on that platform, and the model creation is built to be done by him. GoldenGate has a very high capacity, so you can build quite extensive models. So you can model a full receiver, a full transmitter, but you can also do blocks if you'd like. So you can include a lot of the effects that you would like to see in your system-level verification. Now, these models can be just nonlinear models with no memory effects, or you can include full-featured memory effects, as we discussed in February. And I'm going to talk a little bit more about that later, what that implies. We do support frequency translation. So if you're doing a transmitter or receiver, you have the option to do that in a fast circuit envelope model. And the nice thing is that you get a model that contains all of the information in a single file. So it's very portable. It's easy to share with other people. And the simulation time of the model, once it's created, is quite independent of how long it took to create the model. So what I'm getting at here is that some models for a large system may take a very long time to create, but once that model is created, it can then be exercised very quickly on the system level side to do quite extensive simulation. So let's look at the model usage side. Similar to model creation, model usage now is done by the systems expert. And this is a very important aspect of this flow. I know it sounds a little silly to divide this, but we have flows actually that do model verification or system verification all on the system side or all on the circuit level side, but we've run into issues where you just have the wrong skill set, so the flow is not tuned for who's actually expected to perform it. So what you find is that you have engineers that are uncomfortable in one domain or the other. So here we've got a nice handoff between the circuit level designer and the system level designer to allow them to focus on what they're best at. On the system level side, we're using an extremely fast and advanced data flow engine. This engine has a lot of capabilities, but the key benefit of being a data flow engine is that it's very fast, and you can do a lot of things in not real time, but in time that's fast enough for you to interact with the simulations while they're running. This simulator also has the ability to tie into a lot of different domains. So if you have digital blocks or firmware or things like that, those can all be brought to bear on this problem. So you can have a lot of interaction of different parts of your radio included in this system level simulation. Also available are extensive standards compliant wireless libraries. So if you're sitting there imagining building an LTE advanced source or sink for your verification tasks, you're in luck because you you don't need to build those yourself. That would be quite an error-prone approach unless you've got plenty of time to a big team to put that together. So those are available to you directly in the system-level tool. And you're not limited to one model. So you have the flexibility of, maybe in some cases you would want to model the whole circuit as one piece, or you could mix and match. So you could have each block modeled independently, and different blocks can be at different levels. So you could have maybe a top-down behavioral model where the design's not done, and have another block that's verification, but you could have all the verification blocks in place as well. So you're not limited to just one model. And you're not limited to just one type of behavior too. One could be an FCE model, and you could have other models coming in from other sources. And probably extremely important here is that when you're on the Windows platform, now you have the ability to run full instruments in your simulation. So now you can attach your VSA to the output of your radio that's running in the simulation, and you can demodulate in simulation time while you're doing things. So you can be tuning gains, you can be adjusting the modulation schemes that you're using, and see it all being handled directly by the instrument. So you'll have a good confidence that when you get to the lab, you'll be able to duplicate the results that you have here. And finally, the system-level tool is going to give you warnings or errors to let you know if you're exceeding the capabilities of the model. So it is going to give you some feedback if you're going outside the valid range of the model. Okay. So the final thing that I think is my most favorite part of this flow is that it's easy. A lot of these system-level application flows are quite a challenge to put together, and I'll have to say that that's been a real barrier for some of the flows that I've used. And this particular flow is very easy to do, and I think what it will mean is that more people will pick it up, more people will use it, and more verification will get done ultimately. Okay, so as is probably obvious from this, one of the key elements in this whole process is the behavioral model. So you have your circuit and you build this behavioral model, but if that model doesn't have high fidelity, then this flow is not very useful. And so let's take a look at that. We're going to start with kind of a historical look at what's been done, and then we'll talk about, in particular, memory effects and how those are tied into this model. So we've got a timeline going back here to 1968, I guess, was when AppNote 95 was published for S parameters. I was pretty young then, but I have read it since then. And what you'll see is that there's kind of a long period where S parameters ruled. And S parameters are used for a wide range of things, but they certainly have been used for behavioral verification. Now, of course, S parameter models are not nonlinear, so they're limited to your passive structures. But they have been used for this purpose. And I can say it's been very successful, but even today there are issues, involved with running S parameters, including, creation of S parameters has been not well thought out for the application and things like that. So it does require some discipline even to use S parameters. Now, through the 80s and 1990s, there was quite a bit of effort. There's always been a strong desire to have more black box modeling capability beyond S parameters, something that can handle nonlinearities. And they were given a lot of names over the years, and to be quite frank about it, they never caught on in a big way. I know that they have been used for various things, but it's been quite limited. Now, starting in the 2000 decade, the GoldenGate tool, we started using memoryless models to speed up envelope simulation around 2001. And that was quite a popular capability. Actually, these tools were used quite extensively. And the modeling was all fully automatic. It was actually hidden from the user. In about 2008, 2007, we were successful in getting memory effects modeled in there. In 2008, X parameters became available commercially, both in ADS simulation and in Agilent instruments. And so those have taken a next step. The nice thing about the items on the top here is that they're all open standards and they're supported by measurements. And X parameters have the beauty of being able to model strong nonlinearities, but also they simplify down into S parameters. So they have a clear lineage from their S parameter origins. So I expect X parameters will be the future. Now, the reason we're not talking about X parameters in the rest of this presentation is historical. So the GoldenGate tool is our tool for RFIC simulation, and currently it doesn't produce X parameters. It produces forms of these fast envelope models. We now call them fast circuit envelope models that we can now share outside of GoldenGate into the SystemVue platform. So let's take a look at memory effects for a little bit. We'll review some of the slides that were presented in February, and then we'll come back and take a closer look at this flow. So just by way of definition, I'm going to define memory effects as non-noise circuit characteristics which cannot be described by the steady-state nonlinear transfer function of the circuit. So what am I saying? I'm saying if you build a steady-state transfer function for your circuit that represents its nonlinear behavior, everything that you didn't model we're going to call memory effects except for noise. So, that's been a very popular approach, and as I said, we've had that in GoldenGate since 2001 for speeding up envelope simulation. But there's other effects that aren't included. So things like filtering effects, delay effects, hysteretic effects, these things have not been captured by these memoryless models, we'll call them. The problem with memory effects is that they're quite difficult to capture, and one way to look at that is it's difficult to predict the circuit response to modulated waveforms when you're building models based on steady-state characteristics. So that's been kind of the challenge that we've been faced with for circuit memory effects. For the purpose of our discussion, we're going to kind of group memory effects into two different types. Long-time constant memory effects we're going to call baseband memory effects. And those that tend to be in the band of interest have shorter time constants, and we'll call those in-band memory effects. So let's take a look at what some of these memory effects look like. So we'll start over here with the in-band effects. Things like matching networks or band filtering in baseband that you, or not in baseband, in your band of interest that you have in your circuit could look like in-band memory effects. Transistor transit time could be involved. On the other side, on the baseband memory effects, these tend to be the more insidious ones. They're harder to model, and they can potentially have much larger impacts on your ability to build accurate behavioral models for your circuit. So for instance, your biasing circuits may have low pass characteristics. Same with gain control or DC offset correction, very low frequency response. Also thermal effects or trapping effects if you're modeling those. So these baseband memory effects are in some ways they're different from the in-band effects because they're typically harder to model. Let's take a look at what I mean by that. So if you have a steady-state solver, you're using harmonic balance, let's say, to analyze your circuit, and you want to use it to build a model. Can you see memory effects with your steady-state solver? The answer is yes, you can actually, but it can be tricky. So, let's say you have an amplifier with this effect is called wrapping. We're showing here, but basically you can see the effect of frequency in your band by doing a single tone sweep. So you can just use one tone and sweep it in frequency so that the bottom curve is your highest frequency and the top curve is the lowest frequency. And you can see with this particular circuit, as it compresses, it actually switch. So the gain drops off much faster for the low frequencies and slower for the higher frequencies. And that effect, to capture that, you have to sweep your one tone through the band, and you also have to sweep power at each of the frequencies to be able to capture that. For the baseband memory effects, it's quite a bit more difficult. So to do this, you're going to need one way to do it. There are other ways available, but you're going to need to have something that will simulate the circuit in the band of interest, but also give you some baseband responses. So in this case, we're using a two-tone simulation and looking at the upper and lower intermod products. And when you see a discrepancy between the upper and lower intermod products, that means that there's something going on in the baseband that is different between the two, and those are considered to be memory effects. This is something called resonance, and in fact, it's interesting because it's quite a bit more pronounced in the middle power levels than even at the higher power levels. So you can imagine that this effect is quite hard to characterize and capture, but that's what we're doing with the fast circuit envelope models. So let's take a look at what the models look like. In a memoryless model, it's as I've described. You basically take your steady-state solver and you just calculate AM to AM and AM to PM characteristics in the center of your band at various power levels. So it's a rather straightforward model to build, and to exercise it, you just interpolate into the results and produce your time-varying response to your input stimulus. Now, the model with memory effects is quite a bit more complex. It basically does a superset of what's in the memoryless model, but it includes now two memory models, one for the in-band characteristics and another for the baseband characteristics. And those two models, combined with the nonlinearities at the various frequencies, are included to give you a fairly comprehensive black box model that can handle a wide range of nonlinear and memory phenomena. So let's look at a couple of quick circuit examples. Now this is not in SystemVue. This is still within the circuit simulator, but these are examples that we looked at in February. Basically, I have a power amplifier here, and this particular power amplifier does not exhibit any memory effects. There's no baseband circuitry included. It's just ideal biasing. And what we've plotted here is the output spectrum under high drive levels. And we're using normal envelope transient as our reference. It's in red. It's underneath the curves. And we've built both a memoryless model and a model with full memory effects out of this circuit, and we've exercised those with the same input signal. And you can see that the results for all three cases are quite identical. And what that tells you is that the memoryless model is just as good as the model as normal envelope or the model with memory. And that tells you that this circuit really doesn't have important memory effects, at least not for this particular simulation. So you can actually get away with any of the three simulations and get good results. But what's important to look at is the simulation characteristics. So again, this is for an amplifier. The numbers are different when we look at like a receiver, and I'll show you those in a minute. So envelope transient is our reference time. We'll call it sim speed of 1x. And you can see the memoryless model simulates very quickly. It runs in 7 seconds. It's about 162x faster than running a normal envelope transient. So it's a very attractive approach. If you have a circuit that doesn't have memory effects, you can use these memoryless models quite effectively to speed up your verification. Now, this particular circuit didn't have memory effects, but that doesn't change the fact that you could build a memory model, and we did, and it took quite a bit longer. It took over 40 times as long to build the model, but and the sim time was, what, 13x slower than the normal envelope transient. But it was still 11 times faster than, 13 times slower than the memoryless model. But it was still 11 times faster than running normal envelope transient. So, and that's within the circuit simulator. So it's important to see that with an amplifier, even if you have memory effects that are important, you can still get a nice speed up by using a behavioral model for verification. Now, this next example is one that I would consider exhibits the real limitations of the memoryless model. This is a receiver, and the important characteristic of this receiver is that it has a DC offset correction circuit. And the way that you build a memoryless model for a 0IF receiver results in a model that's extremely inaccurate. So if you look at normal envelope transient is up here at, the signal levels at minus 50 dBV. We're at minus 120 with our memoryless model. So we've got 70 dB of error, and in fact, I would say that's probably the amount of DC offset suppression or the gain of your DC offset correction circuit. So the steady state solver is going to, have that thing fully settled to its final solution. So you're going to get a huge error. Now, on the other hand, if I turn on my model that includes memory effects, I can get a quite an accurate response for this same circuit. It requires a lot more modeling time, actually, but I can build a model that can be exercised quite quickly. So let's take a look at how those times are for that case. Normal envelope transient takes about 1,560 seconds. That'll be our reference time. You get a 111x speed up with the memoryless model, but it doesn't matter, right, because it gives you the wrong answer, so it's quite useless. Now, interestingly, because of the challenge to model this particular circuit, it took a lot longer to model the circuit than it did to simulate it. So in the February discussion, this wasn't very interesting if you're just using the model to try to get a speed up. In this case, if you were just using it to speed up your simulation, you'd be disappointed and you'd decide it was better just to run normal envelope transient. But if you look at just the sim time, now we've got a 42x speed up over what we got when we ran envelope transient. So if instead I'm trying to build a model to export over to a system level simulator, then I've got something that's quite interesting because now I've got a fast simulating model that captures the behavior of my actual circuit. So let's move on and take a look at some of the issues. So I don't know how many of you are from not in the U.S., but anyone in the U.S. should recognize the humor here. This is a simulation general's warning. It's modeled after our Surgeon General's warning on cigarette labels. But it's a little bit tongue-in-cheek, but I really do feel strongly about the issue of sharing models. So anyone who has used GoldenGate in the past to do fast envelope simulation, including engineers here within Agilent, knows that it's very easy to say, okay, I want to run this with a behavioral model and press run, and I get my results quicker in most cases. So what we're faced with, and what I've already seen happening, is that it's so easy to do within GoldenGate that people assume it's the same case when they are sharing the models out to SystemVue users. Well, it couldn't be farther from the truth. When you're building a model to share to another simulator, the simulator no longer has, SystemVue doesn't have knowledge of what, GoldenGate doesn't have knowledge of what's going to be done in SystemVue when the model is exercised. So that's up to the person who creates the model and the person who uses the model to communicate and to build a model that is useful for the specific simulations that it's going to be exercised in. And so, if you're not following, best practices here, you can get into trouble. So let's talk about what those best practices might be. First of all, I think you really need to know the frequencies and the signal levels that you're working with. You need to know the highest and lowest signal levels that you're going to be stimulating the model with. You also need to know the band of interest. So not just the center frequency, but how much bandwidth do you need to capture in your system level simulation before you can produce your model. It's also important to really look at your circuit characteristics. So again, in the past with GoldenGate, you really didn't have to know any of this because the simulator was just going to set up the model for the case that you're running. And that was great, but now you actually have to know something about the model. And if you're the design, or about the design, if you're the designer, you typically will know that. But a lot of times, within Agilent, for instance, we'll get a circuit from a customer, and we need to find out what's involved. So, I recommend that you at least know the AC response of your circuit, the compression characteristics, and you really need to know if the model has memory effects, which is something that's not so easy to do, but maybe you have to run some envelope sims to find out. Once you've built the model, you need to test it. So you can test it within GoldenGate. You can run a simulation right inside of GoldenGate and see if it has the behavior that you expect. Or you can test it within SystemVue. We're not going to talk about it today, but within SystemVue you can run that model, but you also have the ability to run the transistor level view through a co-simulation. And it's a good capability that allows you to do verification of your models within the system level environment. And also, importantly, you need to document the model. So I'm all for self-documenting things. So I like long file names that include kind of a detailed description of what kind of a model it is, what it's modeling, what was the circuit involved, and we also give you room in the model. You can, when you create the model, you can put in notes. So write a lot of notes so that when someone pulls this model in the SystemVue, they'll get some information about what's included there. Very important to have an idea of a model. If you just have a model that's called fce.text, you'll find that tomorrow you may not know what that model was used for. So anyway, just a couple of notes to try to help you to use these models effectively. And while you're simulating in SystemVue, you're going to want to watch for the warnings. So if it's going outside the, like it's going above the top amplitude level that you've modeled your circuit, you're going to start to get warnings, and you're going to want to catch those. Okay, so what do I mean about modeling for to match your circuit characteristics? So let's say we wanted to build a memoryless model for this amplifier that I have response for here. And since the memoryless model doesn't even capture the gain characteristics versus frequency, at the very max, I'm probably going to want to have maybe a band as shown here. Maybe that's 150 megahertz, which is a very wide band actually for a memoryless model. This circuit is very flat. But even at that, I would have to be aware that I'm maybe having about a half a dB of error at the edges of my band. So it probably isn't too bad if that's just intermods that are already 100 dB down. It's probably not a big deal. But just be aware that if and this circuit, by the way, may have baseband memory effects that need to be modeled as well. So the in-band effects are only part of what you have to check for. Now, if you're building a model with memory, you don't have the same limitation. It'll capture all of these effects, but you're going to be specifying in the model creation how wide your modeling is. On the amplitude side, you're going to find that you're not going to want to go 30 dB into compression because you'll have a model that takes forever to create, and you may run into convergence problems in your creation. So you'll have some peak input amplitude that this model is going to be accurate to. And what will happen when your model gets used within SystemVue is it's going to hard clip right at the point where you stopped simulating it during the model creation. So you're going to have to be careful and make sure that you're high enough so the signals that the system level designer wants to use are included in the model that you provided. Okay, so let's take a quick look at the SystemVue side. Basically in SystemVue you have a symbol. It's a polymorphic symbol, and it allows you to do a lot of things with your model. First of all, when you place a model, an FCE model in SystemVue, you'll get a lot of details from the model. So it will tell you some things about the number of amplitude sweep points, the frequency sweep if there was any. In this case it's a level 1, which is memoryless, so there's no frequency sweep. The fundamental frequency that it's modeled at, and the names of the ports that are included. So you've got a lot of details that are available to you. And if somebody had written a note there, you would have a note to look at as well. Now, once you've placed this symbol, you can easily switch between different FCE models. So I could have a model for each corner, for instance, for my radio, or I can have them for different circuit settings. Or even if I'm building a system and I want to maybe, swap in different designs or be able to choose from different designs, I can bring in different circuits, even from different vendors, and run them within my system levels. As I mentioned earlier, I do have the option of co-simulating, so I can actually run the real circuit within SystemVue by co-simulating onto the Linux environment. Now, that sounds great until you actually try to do it. So in the example that I'm going to show later, the SystemVue sim for LTE runs in 3 seconds or something like that. If you run that same simulation with co-simulation, where the circuit is included, and it's a small amplifier, it's not a complex circuit, the simulation takes an hour. So you're going to be quite limited in how much complexity you can have on the circuit level side if you choose co-simulation. That's one of the reasons I'm such a big fan of these fast circuit envelope models. You can also swap in a behavioral model. So let's say your system level designer designs the system with just behaviors of circuits, and then he can transfer in the FCE models to do verification as he gets the designs completed. And maybe you have other views. Maybe there's some digital views, some other types of views. There's quite a bit of flexibility available in SystemVue for this. And what you'll find is that once you put the FCE models into SystemVue, they run very quickly. In fact, I think they run faster within SystemVue than they do when you exercise them within GoldenGate. So here's a quick example. Same circuit that we've shown before. We've got a coded LTE uplink source, and we've got we've actually got a slider here, so we can control the amplitude going into our amplifier. We're modulating up to the RF frequency, and then we're going through our amplifier with memory effects modeled. And one of the nice things here is we're running our 89600 VSA right in the simulation. And so this simulation runs very quickly. Here's 2 results. So the VSA runs on your desktop. It looks just like it would in the real instrument. And with the signal level backed off, you've got a nice clean response, very good ACLR, and you can do 150,000 points in 3 seconds, which is extremely fast. Here's the same circuit with the slider. Now, this was part of the same simulation. Just slide the slider up so that you've got more amplitude going into your amplifier. Now you're compressing very hard. We've dropped ACLR to 23 dBc, and EVM has shot up to minus 21 dB. Again, 150,000 points done in 3 seconds. Quite a powerful verification capability. And as I mentioned, I've run this example in co-simulation form. So compared to doing a co-sim where you have a pipe open to the Linux side, so you can run your system level tools at the same time. This sim takes about an hour, so that's about a 1200x speed up over doing co-sim. And again, that's for a small circuit. So the speed up for a big circuit is going to be much higher. If you're running a receiver or something like that, you're going to find that co-simulation is not really even an option in that case. It's good to have the option for the small circuits just to do verification that your model is working well. Another popular use for SystemVue is for digital predistortion development. So you can build models and try to correct for PA nonlinearities and memory effects, and then test them within SystemVue. So you can work with models of your circuit, or you have the option of actually doing it with real circuits. But in this case, it would make sense to do it with an FCE model. With digital predistortion, you can often achieve very significant linearity improvements, 15 to 20 dB for LTEA, as you can see over here. And you can kind of get assessments. You can try different PAs and see how they work. So the ability to bring in a behavioral model and assess them against your digital predistortion early in the design process is quite a powerful capability. So, okay, well, so let's, one more slide here on digital predistortion. The other thing that's nice about this approach is that it closely mimics what you're doing on the bench. So typically in the past, this was done using a full hardware-based approach, but now you can link to hardware with SystemVue, but you can actually do the whole thing within SystemVue by getting models from ADS or GoldenGate and running them directly within SystemVue. And if you have the full characteristics modeled, then you can have a good idea what you're going to face when you get to the bench. Okay, so let's wrap up. So we've presented a new approach for verifying system-level behavior of a modern RFIC, and the key to it is using fast, accurate data flow type models, and these can be created directly from your circuit simulation tool. And those models can include full memory effects so that you can model those in case they're included in the circuit characteristics. We'll talk a little bit about the use of behavioral modeling in the past for modeling linear as well as nonlinear behavior. And what we see is that we really are converging on good quality solutions that model very accurately the effects that are available in your circuits today, and those are even becoming available in your instruments and in your standards so that we can use these effects widely. So that's why we're having training. We're starting to roll this out so that people can take advantage of these capabilities. I've cautioned you about sharing models, so especially for the GoldenGate users out there, if you've used fast envelope in the past to speed up your simulation, don't think that producing an FCE model is the same as running fast circuit envelope. It takes quite a bit more forethought and planning. You can produce a very good quality model for use within SystemVue, but you do have to know more about your circuit and about the application in SystemVue before you produce that model. We talked about it, just a couple of examples. There's many, many more things this could be used for. This is new to us too, and we're just starting to explore what we can do with this. But I do think it's quite powerful, and particularly I'm excited about the ability to run these simulations with the accurate behavioral model for the circuit and be connected to the instruments and see how the instrument is going to demodulate the signals and figures of merit that it's going to measure. So what I'm hoping is that, given the ease of use and the power of this approach, that you, the customer, will be able to do quite a bit more system-level verification of your radios than you used to be able to do in the past. So with that, I'll say thank you, and I'll turn it over to Carmina.
Thank you, George. Thank you very much. Okay, in a moment we'll begin today's question and answer segment. And remember to complete the survey that will automatically launch at the end of the webcast. And as I mentioned at the beginning, by submitting the survey, you'll be providing us with valuable information on how we can offer you more and better webcasts in the future. So please take a moment to do that at the end of the webcast. You may have noticed there's some chat going on, and Frank Dettori, one of our wonderful panelists, did not realize that some of the questions were asked, but you all can't see those questions, so we'll try to straighten that out. But let's move on to the question and answer portion of the event. And as a reminder, if you have a question, you can type them in the chat window now and select all panelists. We'll try to answer everyone's questions live, but if we run out of time, we'll respond to the remaining questions via email. Okay, George, here is the first question from Emmanuel. How about behavioral models for design centering purposes? The time spent to create a memory model can be traded for multiple simulations, for instance, different stop times and swept parameters.
I'm here.
Oh, okay. Yes, I know you're thinking.
Yeah, so for design centering, it depends. We do offer other flows. Now, let me be clear. This isn't the only system-level flow that's available. We have flows that operate entirely within Linux. So if you've got a lot of iterative simulations on the circuit that need to go on for centering, those could be done. We currently have a Ptolemy-based flow on Linux that allows you to do that, and later, either later this year or earlier next year, we're going to have a SystemVue-based flow that will be able to run within the Linux environment. Again, those have pluses and minuses. You can also, if it's sinusoidal, you can do a lot of that just directly within the tool. So you have to take each problem or task as it goes. Clearly, behavioral modeling is not the key for every. It's not the solution for every case. And I think you do have to get to the point where there's something difficult to do in the circuit simulator before you're going to want to create that model. So good question.
Thanks. Emmanuel, if you have follow-up questions, you can go ahead and enter them in chat. This is a question from Gabriella. I currently use MATLAB for system-level modeling. How can I use the FCE model with my existing MATLAB code?
That's a good question. Maybe Frank would answer that better. I'll just say that there is capability within SystemVue, I'm pretty sure, to handle MATLAB-based models. Frank, can you unmute?
Yes, can you hear me, George?
Yeah, yes, I can hear you.
Yeah, so basically, you can confirm if this is incorrect. MATLAB does not currently support the FCE model, but as George indicated, SystemVue allows importation of MATLAB scripts directly, and along with the other features that George mentioned in this webcast, you can bring your MATLAB IP directly into SystemVue and utilize that platform and that framework to do the RFIC verification that was outlined in this webcast with your MATLAB code.
Thank you, Frank.
Okay, thanks. Here's another question about FCE. This is from Mac. Do FCE models contain noise?
Currently, they do not. We do have, it's a popular request from customers for FCE models, and it's interesting because if you're in GoldenGate and you're doing fast envelope simulation, you can include noise in your simulation when you do that, but the noise is not captured directly in the model. It's handled through a different method in GoldenGate. So what I'm getting at is that we're hoping to use a similar mechanism to include noise effects in your FC models in the future. So I guess the answer is no currently, but it's a popular request, and we hope to be able to do that in the future.
Thanks, George. Okay, here's another question from Naomi. Does GoldenGate produce X parameters?
No, we're probably the only tool within Agilent EEsoft that does not produce X parameters currently, but we will in the future. I can't give you a date for that. GoldenGate is about to start supporting simulation of X parameter models in the upcoming release later this fall. So not yet, but it is coming. X parameters are coming to all Agilent products in the future, I believe.
Okay, great. Thank you. Here's a question from Henry. How do you verify that the model with memory accurately captured all the memory effects in your circuit?
The best way to do that is to take the approach that I showed in the earlier slides, where you actually run a modulated waveform through your circuit, and it needs to be representative of the characteristics or the case that you're interested in. Run that modulated waveform through normal envelope transient and through your model and compare the results. And if the model is effective, the results should be very close. So, and when I say results, you need to be looking at whatever figure of merit it is that you care about. So you can't just say, well, the spectrum looks okay if you care about EVM. So you kind of need to be monitoring whatever it is important for your particular application. So it's a good question, and I think that's the key to getting the value out of these behavioral models, is they need to model the behavior that's in your circuit, and it needs to be done accurately. So it's important to go through that verification step before you start using it to verify your circuit.
Okay, thanks. Henry, if you have follow-up questions, go ahead and enter them in chat. Now here is the question to the answers that Frank Dettori posted. There was a question from Luis. We don't have GoldenGate or SystemVue. Can we run similar simulation in ADS with the right wireless library? And Frank, if you wanted to go off of mute, you can answer that live. I know you put it in the chat, but just to have the answer live.
Yeah, so the answer that I chatted into the chat window is basically you can run Cadence netlist directly in ADS, or if you capture your circuits directly in ADS, you can certainly take advantage of the Ptolemy-based simulator and co-simulation native in ADS to do the same types of verification that Paul was outlining here for GoldenGate. I guess the key difference is that GoldenGate, as I mentioned in chat, natively sits within Cadence Virtuoso ADE and runs advanced harmonic balance simulation and circuit envelope types analysis directly in Cadence without having to leave that platform. And the flow and methodology that Paul described today allows a Cadence Virtuoso user that's taking advantage of GoldenGate to export these models into SystemVue for verification.
Thanks, Frank. Okay, let me go back to the questions and let me scan for some more. Okay, here's just kind of a follow-up to that GoldenGate question that we asked. Does SystemVue accept X parameters? So that's from Xiao. I don't know, Frank, if you want to answer that, or George?
The answer is yes. Correct, Frank?
Yes.
Great. Okay, looks like we have time for a few more questions. Let me go ahead and check in the chat. Frank, was there another one that you were trying to answer that I didn't see, the answer was, or?
I believe there was a question from, if I'm pronouncing it correctly, Zhu Feng, and he was asking if ADS supports the fast circuit envelope model, and the answer is no, it does not today.
That's a good question, and that's a popular request actually is for this FCE model capability to be added within ADS, and we're currently looking at that. We don't have a commitment to do that yet, but it certainly is something that we will consider. It will, a lot of this will depend on X parameters. As you may know, X parameters now, the theory includes the memory effect as well. So it's possible that ADS will simply continue to support X parameters, and we will just have to see as that plays out. So not currently, but maybe we'll have memory effect support from ADS in the future.
Okay, here is, I'm going to have to ask this one question because this is all that we have time for. How does, this is from JE, how does the 89600 VSA work with SystemVue?
So the interface we have with the 89600 vector signal analyzer in SystemVue is very similar to what we have in ADS. So you can execute dynamic measurements on SystemVue simulations using the 89600, and you can use the fast circuit envelope model as part of one of those simulations. So you can use the 89600 to demodulate a signal that's passing through a fast circuit envelope model, so you can monitor any distortion, EVM degradation type effects.
Okay, thanks, Frank. Okay, it looks like that's all of the questions that we will have time for today. We will follow up with the rest of the questions by email. And George, I'd like to get some closing comments from you.
Well, I'd like to say thank you to everyone who has attended today. We look forward to the possibility of working with you on any applications you may have. I've got a slide here that gives you some links. If you want to find out more about GoldenGate and or SystemVue, we've got our links to those pages that you can type in. And Carmina, do you happen to have the link that you could put in chat, or I guess it's going to get sent out by Emily to all the participants for all of the webcasts that we have. So if you wanted to go back and look at the memory effects cast that we did in February, there will be a link available to you for that as well. True?
Yeah, I just went ahead and put in the chat again. You got it.
Okay, great, thanks.
Okay.
Contact your ESOF field representative if you need more information, or you can certainly contact Frank or me at the email addresses that are shown. So thank you again for your time.
Okay, thanks so much, George. Thanks for your presentation. As we wrap up today's presentation, remember that we will email you a link when the on-demand version and the PDF slides are posted on our website. You're also invited to register for our next webcast, How to Make Your Designs More Robust. I'm going to go ahead and advance the slide there. This is our 12th webcast in the Innovations in EDA webcast series brought to you by Agilent Technologies. If you're viewing the on-demand version of this webcast and have a question about any of the material, please email George directly at george_estep@agilent.com. I'd also like to remind on-demand viewers to complete the webcast survey that will automatically launch at the end of the webcast. Thank you again for attending today's event, a model-based approach for system-level RFIC verification, brought to you by Agilent ESOP. The copyright of the presentation materials is owned by Agilent Technologies. For a current schedule of live and on-demand events, please visit us at www.agilent.com/find/events, and you can use the URLs on the screen for a look at our recorded webcasts. I'm Carmina. Thank you for joining us, and have a great day.